Imagine two enormous cities. Not just cities, but whole continents, each with billions of people, all moving at their own pace. Now imagine these two continents are hurtling towards each other through a vast, empty ocean. What happens? You'd probably picture a massive crash, total chaos, buildings crumbling, everyone screaming. It sounds terrifying, but when two galaxies collide, it's not like that at all. Not even close. It's one of the most common, grand, and beautiful events in the universe, and it's far less violent than you might think. We call it a collision, but that word can trick you. It makes you think of cars smashing together or planets hitting. That's just not how it works in space, not on this scale. See, galaxies are mostly empty space. It's hard to wrap your head around, but it's true. Our own Milky Way galaxy has hundreds of billions of stars. And those stars are huge. Many of them have planets, just like our sun has Earth. But the distance between those stars is enormous. It's mind-bogglingly vast. If the sun were a grapefruit in New York City, the next nearest star, Proxima Centauri, would be another grapefruit in Los Angeles. That's how much empty space there is between stars. So when two galaxies come together, what actually collides? Not the stars, mostly. It's incredibly rare for two stars to actually hit each other. Think about it. If you throw two buckets of sand at each other, most grains of sand will just pass right by other grains. They won't hit. Stars are like those grains of sand, but with even more space between them. Instead, a galaxy collision is more like two clouds passing through each other. Huge, incredibly spread out clouds. And gravity is the main player. It's what starts the whole show, and it's what directs the dance. The process begins long before the galaxies get close. From millions of light years away, their gravity starts to tug at each other. Each galaxy is a huge collection of mass stars, gas, dust, and a lot of dark matter that we can't see but know is there. All this mass has gravity, and gravity pulls things together. So, as they get closer, they start to speed up. Imagine two slow-moving giant whirlpools in the cosmic ocean. They feel each other's presence. They start to distort. This is called tidal force. It's the same force that causes tides on Earth, where the moon's gravity pulls on our oceans. But on a galactic scale, it's far more powerful. These tidal forces stretch and pull on the galaxies. They draw out long streams of stars and gas, creating what we call tidal tails. These tails are beautiful, glowing tendrils that stretch out into space, sometimes for hundreds of thousands of light years. They're like cosmic scars showing the ongoing struggle between the two gravitational behemoths. You can see pictures of these in distant galaxies, and they look like something out of a science fiction movie. But they're real. Then comes the first pass. The two galaxies swing past each other. They interpenetrate, their edges touch, and then their main bodies start to mix. This is where things get really interesting. While stars mostly avoid direct hits, the gas and dust clouds within the galaxies are different. These clouds are much larger and much less spread out, relatively speaking. When two big gas clouds from different galaxies encounter each other, they do collide. They smash into each other, and when gas clouds hit, they don't just bounce off. They compress, they heat up. And this compression is like hitting a cosmic on switch for star formation. Suddenly, vast amounts of gas and dust are squeezed together, reaching the densities and temperatures needed for new stars to ignite. This leads to a massive burst of star formation, a starburst. These starburst regions glow incredibly brightly, lighting up the merging galaxies with the birth of millions of new stars, including many massive, hot blue stars that burn fast and bright. Think of it, the very act of colliding creates new life, new stars. It's a creative destruction, a beautiful paradox. Meanwhile, the supermassive black holes at the center of each galaxy also get involved. Almost every large galaxy has one of these behemoths in its core. When the galaxies pass through each other, the black holes get jostled. New gas and dust get funneled towards them. As this matter spirals down into the black hole, it heats up to incredible temperatures, forming a super bright disk called an accretion disk. This can make the black hole active, spewing out powerful jets of energy and radiation. We call these active galactic nuclei, or quasars, if they're particularly bright. They can outshine the entire galaxy they live in just for a time. It's like turning on a cosmic lighthouse in the very center of the chaos. After this first pass, the galaxies don't just keep going their separate ways. Gravity pulls them back. They slow down, perhaps even reverse course a bit, and then they start falling towards each other again for a second pass. And maybe a third. It's like a very slow, majestic, cosmic dance. Each pass further mixes the stars, gas, and dark matter. The galaxies lose their original distinct shapes. Spiral arms get torn apart, disks get warped. The overall shape of the galaxies changes dramatically with each interaction. What started as two distinct spirals or ellipticals might become a messy, irregular blob, then a stretched out, lopsided form, and eventually, after many passes and much mixing, they merge into one larger, often more spherical or football-shaped galaxy. This final merged galaxy is usually an elliptical galaxy. Why? Because all that gas and dust that caused the starburst eventually gets used up. It's either turned into new stars, or it's ejected out into intergalactic space by the powerful winds from those new stars, or the active black holes. Without fresh gas and dust, new star formation largely stops. The remaining stars in the new galaxy are old and red, and they orbit the center in random, complex paths rather than in the neat, flat disk of a spiral galaxy. That's why ellipticals are often called red and dead. They don't make many new stars anymore. And what about those central supermassive black holes? As the galaxies merge, their black holes slowly spiral inward toward the new center of the combined galaxy. This is a very drawn-out process, taking millions or even billions of years, but eventually they will meet. And when two supermassive black holes merge, it's one of the most powerful events in the universe. They create ripples in space-time itself called gravitational waves, which we can now detect here on Earth. Imagine the combined gravity of two of these monsters finally joining forces. So if you were living on a planet around a star in one of these galaxies during the collision, what would you see? Well, you wouldn't feel anything. The distances are too vast for physical bumps or shakes. Your planet would stay with its star. But the night sky would change dramatically. At first, you might see the approaching galaxy as a faint, fuzzy patch, growing larger over millions of years. Then, as it gets closer, it would start to fill more of the sky. Its spiral arms, its bright core would become clear. During the actual interpenetration, you'd see stars from the other galaxy moving across your sky. The constellations you knew would get messed up as new stars appeared and old ones shifted their positions relative to you. You might see huge bursts of new star formation, bright nebulae, lighting up parts of the sky like cosmic fireworks. It would be a breathtaking slow-motion show that would last for billions of years. Your star and its planets would mostly keep going as they always have, but its orbit around the galactic center would change. It might get tugged by the gravity of the other galaxy. It might get slung into a different part of the new merged galaxy. A small fraction of stars, those unlucky few that get too close to the gravitational slingshot of the merging cores, might even get ejected entirely from the galaxy, doomed to wander intergalactic space alone. But for most stars, it's just a change of address within a much bigger new neighborhood. The unseen dark matter also plays a huge role. We don't understand dark matter perfectly, but we know it makes up most of the mass of a galaxy. Each galaxy is embedded in a huge halo of dark matter. When galaxies collide, these dark matter halos also merge. They pass through each other, and their gravity influences the distribution of the visible matter, the stars, and gas. The dark matter acts like the invisible scaffolding that holds the whole galactic structure together and guides its merger. Our own Milky Way galaxy is on a collision course, not with some distant random galaxy, but with our closest large galactic neighbor, the Andromeda galaxy. Andromeda is a giant spiral, even bigger than the Milky Way. It's currently about 2.5 million light years away, and it's rushing towards us at about 110 kilometers per second. But don't panic, this isn't happening tomorrow, or next year, or even in the next million years. This cosmic event will begin in about 4.5 billion years. By that time, our sun will be much older, perhaps already swelling into a red giant. Our solar system will still be around, but it's hard to say what Earth will be like. When Andromeda and the Milky Way start their dance, we expect a spectacular show. The night sky will be filled with the approaching Andromeda galaxy, growing larger and larger. The first pass will be dramatic, with new star formation and tidal tails stretching out. Eventually, after billions more years of interaction, our two spiral galaxies will merge to form one larger elliptical galaxy. Scientists have even given it a name, Milkomeda. It's a strange thing to think about. The slow, beautiful end of our galaxy as we know it, and the birth of a new one. But it's a natural part of the cosmic cycle. Galaxies aren't static islands in space. They grow, they evolve, they interact, and these interactions, especially collisions, are a major way that galaxies grow bigger and change their shapes over billions of years. Looking at these collisions teaches us so much about how the universe works. It helps us understand how the giant elliptical galaxies we see today likely formed from the mergers of many smaller spiral galaxies in the past. It shows us how star formation can be triggered on a grand scale. It reveals the powerful influence of dark matter and supermassive black holes. It's a key piece of the puzzle of galaxy evolution. So, when two galaxies collide, it's not a violent, destructive smash up. It's a slow, majestic gravitational dance. It's a messy, beautiful waltz that takes billions of years. It's a process of creation and transformation, and it shows us just how dynamic and alive our universe truly is, constantly changing, constantly rebuilding itself on scales that are almost impossible for us to imagine. It's a cosmic ballet, always in motion, always evolving.